Okay, so last time I had sort of done part B of this problem, not part A. But one of the things I kind of would like you to remember from last time is that we had a rod at an angle of 57 degrees with respect to the horizontal. That 57 degrees, or the rod, the bar is released. It's 3.2 kilos. And determine its angular acceleration if at that instant under two conditions. And we did the surface is smooth. And if you remember that, we had this. We did all of the moments about point G, and we did sum of forces in X, sum of forces in Y, and we calculated out the acceleration of point C, which is equal to G plus AC with respect to G, did all of that. We got 16.96 rads per second squared. We didn't look at the first case. In the first case, we could do sum of moments about C. And in that case, we now have a force of friction that's been added to the problem. We have a normal force which is acting upwards. We have a weight which is acting downwards. And all we need to do is do sum of moments about that point of contact. It gets rid of the force of friction and normal force. So mg L over 2 cos of theta equals 1/3 ml squared alpha. And from this, you would get alpha is 3g over 2l cos of theta. Where did that 1/3 come from? Parallel axis theorem. So you remember that with the parallel axis theorem, you have two conditions or cases that you really should remember. One, which is about the center of mass, which is 1/12 ml squared. And for this case, it's about the point C, and if you do the parallel axis theorem, you'll find it's 1/3. And if you don't want to do that, you can memorize pinned slender rod. And what you end up with is alpha is equal to 8 rads per second squared. So same condition, same problem, different result. So alpha was 17 rads per second squared, and alpha is 8 rads per second squared with the introduction of friction. The other thing is that I did not, in that particular problem, use that pinned end. Because the point C that's in contact in a frictionless case is going to slide. And the parallel axis theorem will not work. So one of the things to be aware of is that, yeah, it's all tied to physics, and it's, you know, if you have a pinned end, if you do all of the things, you can do it with a parallel axis theorem, or you can just transfer the moment that's associated with the linear acceleration of the center of mass to the pinpoint. But you cannot do that when you have something that is moving at an end. And so you do all of your calculations about G, not with respect to C. But in the other case, you were told surface is rough and the bar does not slip. So it's important to sort of recognize those two sort of cases, because those cases become very important. And it becomes something that actually drives you a bit crazy, because you want to know when exactly to use the parallel axis theorem. So it's not a universal case. Oh, I know. Okay, so what I've done so far, I haven't done any problems where we have rolling with slip. Because one of the problems in kinematics has been, in kinematics, I tell you, hey, it's slipping or it's not, but I don't do anything with that. And so 90 or 100% of the problems in kinematics were rolling without slip. But once you know the force, you can sort of determine whether or not you actually have rolling with or without slip. So here I have a ball, a wheel. I'm pulling at the center with a force of 180 newtons. I have a mu sub s, which is 0.2, a mu sub k, which is 0.15, and I'm asked to find alpha of the wheel. So all I'm trying to find here is what's happening. So if I look at it, I have G here. I have a force there. I have N, and I have force of friction. And the distance between the two I call it radius of G, R to G. So the center of mass here is G. RG is the distance from the point of contact, the radius of the wheel, to the center of mass. Okay, so that's kind of okay. Forces of friction generally are really straightforward to, or sorry, forces are generally straightforward to write for these problems. You try to imagine much more things happening, but they don't. So I have a terrible looking eye. And I can start to say certain things. Maybe I won't use red. The first thing I'm going to do when I solve all of these problems is the same thing, which is to say I have no slip at the very beginning. And then I'm going to check and see whether the results convince me that I have, in fact, met the conditions for no slip. So in this case, I have a force at the center of the disk that's pulling on it, wheel of P, which is 180 newtons. I have force of friction, which is opposing the motion. The motion is going left to right, but the wheel itself is rotating in a clockwise direction. So the clockwise direction determines the direction of the friction force for now. Normal force is acting up. That is an IG. Now for disk, I already know it's 1/2 mr squared. I'm not going, again, you don't have to rederive everything. You do have to know slender rod, disk, and a hoop. And for a hoop, of course, it's mr squared. But for IG of a wheel, a disk, it's mr squared, 1/2 mr squared. And so you end up here with 3 alpha, and here with 0.225 alpha. Of course, I didn't keep the units. All right. So let's take a quick sort of detour and go back to this whole idea of wheels rotating with and without slip. We can always treat an object as if it's translating with respect to, say, a center point. And the center point here, I know what that is. it's going to be going with velocity g. So if I want to just say velocity g plus velocity c with respect to g, I can say everything is rotating about g, in which case the rotating direction is here. So when I add this and this, these two terms will disappear. This is just from the kinematics. And so these points, and I want to do this drawing, it's going to be 2vg, this will be vg, and this will be 0. And again, one of the things you have to sort of accept is that all of the rotation is occurring around the point of contact, not about the center in reality. So the absolute motion is always going to be with respect to that. So now I have everything I need. I have normal force, friction force, I have pulling force, and G, and I forgot mg. So sum of moments about C are equal to I, G, and remember, C is that point of contact. IG alpha plus MAG RG. So if I look at that, I say, okay, look, I could do this two different ways. And again, I know that I have 0 velocity at the point of interest. So C is a point of interest, and I can use the parallel axis theorem. Or if I don't want to use the parallel axis theorem, I can just go straight ahead. And so if I do that, I just am going to end up with IG alpha plus MRG alpha times RG, because I have a fixed point of contact. Now, I can reorganize that a little bit better, and I come back to IG plus MRG squared alpha, which is the parallel axis theorem. All right, so I have all of that. Everything's there. All that's going to work. The only thing that I have a pulling force of 180 newtons, which is going to the right, acting through the center. I have the normal force, I have the friction force, and I have the weight. And all of those have 0 moment with respect to point C. So if they have 0 moment with respect to point C, you can do just this, P times RG. And you end up with alpha equals to 40 rads per second squared. So you take all of that, you just put the numbers in. And so for IG, all the terms that you have, you put them back in, you'll end up with the correct term for IG, or alpha, excuse me, alpha. So alpha ends up being 40 rads per second squared. Sum of forces in X is MAGX. P plus force of friction equals MAGX. Force of friction equals 60 newtons. Yay, I'm done. So I've calculated the force of friction. I've done all of the balances in the x direction, and x is just in the direction of motion. So xy. But I really haven't done anything yet. I need to sort of see force of friction max is equal to mu sub s mg. Because if I look at the sum of forces in y, it's normal and weight. So if the normal and weight are there, and they're both sort of balanced out, I end up with a force of friction max of 40 newtons. So this is one of the first cases you have with slipping occurring. So you've gone through all of this effort, you've kind of confirmed what you had sort of an assumption, it didn't work. So what you have to do is go back again and do the same thing all over, but with one kind of crucial difference. So again, everything looks the same. You have P, mg, you have a normal force, you have, I'm just going to put it out here, force of friction. And if you put all of that together and you do the same thing, you have Ig alpha and you have MAG and you have all of that equals all of the forces that are being applied and all the rest. So sum of forces in y is again mass times acceleration of g in y, and n minus mg equals 0, n equals mg. So that's the weight is equal to the normal force. So that hasn't changed. But what has changed is your force of friction. Force of friction now is equal to mu sub k times n, which is 0.15 times n. And the other thing that I know is that Ag does, Ag does not equal Rg alpha if I have slip. So I can't use the parallel axis theorem anymore. I can't do a lot of things, but I already know what the force of friction is because it's maximized. So remember, three cases, no slip, impending slip, and slip. And in the slip case, it's always going to be force of friction equals mu kn. So once you have that, you have Ag equals Rg alpha. Agx, you solve for. So you know what P is, you know what the force of friction is, you know the mass of the wheel, you just don't know Agx. So you end up with 7.53 meters per second squared, which is the tangential velocity also. So I have to do some moments about g. Same problem as before. In the first example, we were looking at that rod that was falling. And in the first example, part of the example that I did Monday, I had done everything about g, and I hadn't explained why. Today, we sort of talked about it. But when I looked at a point with no slip, I could do moments about c. But in this case, I do have slip. And because I have slip, I have to do moments about g. So in this case, I get lucky. In the sense that if I look again at all of the forces acting about g, P doesn't cause a moment, normal doesn't cause a moment, weight doesn't cause a moment, but the only thing that's left is force of friction, which does cause a moment, and it's acting a distance r sub g away from the center. And And in this case, it's going to be a clockwise rotation of about 20 rads per second squared. I did that. And it's negative because it's clockwise. So as you're going through these problems, try to make sure, and I am trying to make sure that as I update my examples, that I keep to a standard coordinate system because things get messed up otherwise. As you found out in problem 5 from assignment 7, if you don't have a standard coordinate system, things get messy. All right, so got that. Okay. Any questions on this one? Yeah, because when I did point C, so at the very beginning of the problem, so just maybe one quick thing. No. Wait. Oh, I didn't tell you what alpha was. So alpha in this case is 40 rads per second squared. In the case of no slip, I have essentially a fixed point and I can do all of this thing relative to that point. And if I do that with a parallel axis theorem, it's the same thing as if I just took this and I have it rolling along. And in this case, I have an acceleration g, and I have an alpha associated with that point. But that point is fixed. So I can say the sum of moments about point C, whatever it is going to equal mag times L over 2 plus alpha Ig alpha here. But if I look at that Ig alpha, it's a slender rod. I can write it out, and I can write 1/12 ml squared. And I'm actually going to make one other substitution. L over 2 alpha Ig alpha. So if I have that case, I have Ig plus ml squared over 2 or 4 times alpha, right? So if I have that case, that actually is the same thing as going with the parallel axis theorem. Right, so the parallel axis theorem would be, I start with this problem, and if I started with this problem, I'd just say Ig plus ml over 2 quantity squared times the quantity alpha is equal to sum of moments about C. So I could do it with both of those cases. But now let me introduce a translational velocity. Say I put that on a pair of skates. I just let it move. So same problem. I'll leave it as AG. And I have an AC at the bottom here. let's say that. The problem is AC does not equal L over 2 AG divided by RG. So what I actually have in terms of solution is I'm going to have to say that AC is equal to AG plus AC with respect to G. And once I do that, I no longer can make this sort of assumption that I had with the parallel, or with just the direct physics. And once I lose the direct physics, I can't use the parallel axis theorem. So as you're looking at these problems, so the two first, the only two examples in this lecture so far, are kind of helpful to sort of think about what exactly is happening and what's the parallel axis theorem telling you. It's not creating new physics. It's just sort of giving you a quick way of doing a transfer. But it doesn't work if you have a relative acceleration or a relative velocity between points. Any other questions on this? Okay. You did that one? Don't want to do that one. Oh, pulleys. Maybe I don't do the threading of the spool. So let's look at threading of spools. So one of the things you'll notice, this is the last lecture on rigid body kinetics directly, so the second law material. Tomorrow, I'll be talking about work energy. So there'll be another 3 lectures on that. Following that is momentum. And today we're sort of going through a few examples because I find it's really helpful to understand the applications more than the formulas. If you look at all of the free body diagrams that I've drawn today, they're very easy. Intuitively, they're hard. You want more in them. But actually drawing what you have is not that bad. All right, so the main condition for rolling without slip is that the friction force does not exceed the maximum possible for a coefficient of friction mu sub s. That you know. The cord is wrapped around the inner hub of a wheel, and it's pulled with a force of N, okay, whatever, or T. Okay, I think I forgot to put the value. Wheel has a mass of 350 kilos and a radius of gyration of 1.7 meters. So you can see it's 1.5 meters to the inner hub, 2 meters to the outer hub, and radius of gyration is something that you really need to know. Mu sub s is 0.33, mu sub k 0.29. Determine the acceleration of g, the angular acceleration of the wheel, and the tension T in the cable when the spool is released from rest. For 2 cases, cord is attached at the top and the cord is attached at the bottom. Given theta is equal to 27 degrees with respect to the horizontal. And, okay. And this is what I'm talking about when I say the free body diagrams are not difficult. Often you want more to these things than what you have. Now, the other thing, too, is I don't know if you remember, I showed you a whole bunch of contact cases where a rope was attached to a wheel and you had definitions of the slip and no slip condition, and I, for the life of me, cannot remember which lecture that was, but it was only a few ago, probably in the kinematics. So I have y acting down the down. I have force of friction acting, force of friction acting down the ramp. I have normal, I have weight, and I have tension. And tension is at the bottom. So force of friction, or sorry, forces in the x direction. I have force of F, force of friction, which is acting down the ramp, which is how I've defined my positives. I have tension acting up the ramp, which is how I've defined negative. And I have a component of weight, which is going to be sine theta, which is acting down the ramp. If I look at the forces in the y direction, I have normal minus the weight component acting in the y direction as defined with this axis. And again, you'll notice that normal is acting upwards, aligned with y, and mg cos theta is acting downwards, which is negative. Okay. I think I'm going to have to sort of spread this out a little bit. And again, here I have a case of force of friction times R outer. So force of friction is here. I'm looking at about y. It's causing a clockwise rotation. And here it's also causing a clockwise rotation. And you'll notice that in this case, I've messed around with the positive direction, and it's not counterclockwise in this case because of the way I've oriented my x. So you got to look at your x, you got to look at how you've defined things, but there you go. So if I continue with that, I've got mu kn minus t plus mg sine theta mr inner alpha of the spool. I have n minus mg cos theta, which equals 0. And finally, I have mu kn r outer plus tr inner equals mkg squared alpha of the spool. Okay, so just a couple things. What's happening here? I want mass times acceleration of g of x, but I didn't do it about the point of contact of the wheel to the floor. I did it about the point of contact with the rope. And so the rope is your no-slip condition, not the point of contact with the ground. And so you can't have 2 points of no slip. So you have to sort of look at what your problem is, and usually 99% of the time, unless we want to mess around with you, we'll tell you that it's probably there. But in most cases, even with the definitions that we have been using, we have tended to say the rope is the point of contact, and that's the no slip point of the wheel.
Is that why you were able to substitute when you went from like the red equations to the blue equations? You substituted.
Yeah, just let me go back to those before we talk. So in the red equations, I have everything. The important sort of substitution I've made is, first of all, the standard substitution that there is no acceleration in y. And so there's no acceleration. Y tells me what the normal force is, and I can use that in my x equation. T remains unknown, but the AGX is where I did make that substitution and say R inner alpha spool, as opposed to, say, a case where I might be looking at a wheel without a rope around it, in which case I would have used R outer. So it's important to sort of recognize that's how that term's going in. The other thing that's important is that I'm using the radius of gyration here. So this term is the radius of gyration. So I'm using, again, I'm pretending, and you'll see this on old final exams, we will give you a radius of gyration, say, okay, it has a radius of gyration of 1.7 meters here. And then you have to know that that's the equivalent to making whatever material you're looking at a hoop of radius k sub g. And I write too big. Okay. Don't know if he's. And T is equal to mg mu sub k kg squared plus r inner r outer All right, so I'm just solving these in variables. It's okay. You probably wouldn't do it like that, and it wouldn't be as big an equation. But again, if you're solving these problems, it's often helpful to keep variables as long as you can comfortably. But if you don't want to keep variables, keep units. And units help you a lot in solving problems. So you have alpha the spool, tension for the system. Okay, so in this case, so for case 1, all right, so I'm jamming everything in that I can, but I have 1893 newtons for tension. I have minus 1.5 rads per second squared, which tells me it's going in the counterclockwise direction, which makes sense. It's probably going to fall. And AGX is a positive 1.58 meters per second squared down the ramp because of the way I've defined all of this. And again, you got to be careful. If you play games with your coordinate system, you play games with all of everything. So I try not to do that too much. I'm trying not to do that anymore, but there you go. So the second case was basically shifting that tension from, or the cable from the top or the bottom to the top. And in the process of doing that, keeping to the same coordinate system down the ramp, and x is positive downwards, y is positive away, and of course you're going to end up with positive directions here. And so you can do forces in x, and you have force of friction negative t plus mg sine of theta equals magx, sum of forces in y, n minus mg cos theta equals magy, sum of moments about g, minus f of f, r outer, plus t r inner equals ig alpha of the spool. So a couple things. So you'll notice that I flipped the direction of the force of friction at this point. I'm kind of assuming that it's going to be rotating in a clockwise direction. And because of that, it's going to be acting up the ramp. So that's the difference here between case 1 and case 2. So I have, because of that, I have a negative force of friction. I have a negative tension, but the tension hasn't changed because it's still acting up the ramp. And when it's acting up the ramp, I have weight which is acting down the ramp. That's positive still. And I have magx. For the y terms, it's going to end up being the same. N minus mg cos theta equals magy. And finally, the one difference here is that unlike the previous case, the friction force here is causing a counterclockwise moment. And because it's causing a counterclockwise moment, that term becomes negative. This term, when it rotates and applies a force about g, causes a clockwise moment. And again, clockwise in this particular problem is positive. So in that case, that term is positive, and I have Ig alpha spool. And if I sort of put all the terms together and do all the same things, maybe I'll do one more step. I have sum of forces in x, mu kn minus t plus mg sine theta equals m r inner alpha of the spool. Sum of the forces in y, and sum of moments about g. Okay, so I have all the terms, I have everything there, and I'm just substituting in. And of course, the only thing that's different in this particular example is that, or no different, is that the acceleration in the y direction is 0. All right, so I end up with some terms, n equals mg cos theta as before. Alpha is equal to g r inner sine of theta minus mu sub k r outer minus r inner cos of theta all over r inner squared plus kg squared. And tension is equal to kg squared sine of theta minus mu sub k kg squared plus r inner r outer cos of theta all over r inner squared plus kg squared multiplied by mg. All right, what a mess. So what does that translate to in the difference between the two problems? I'll leave that there for a second. Tension is equal to 895 newtons. Alpha of the spool is equal to minus 0.43 rads per second. And A of the spool is 0.639 meters per second squared. Okay, so there are significant differences between the two results, and it's kind of important to sort of think about them as you're going through the setup of the problem. But the really hard part of this problem is not that. The math is easy. I put a lot of variables in there. It's kind of crazy. But the calculations themselves are stuff that you've done and you're very comfortable with. Where you may have, where you kind of get lost sometimes, and what is the trickiest bit of this, is one, to recognize that you have slip on the ground. So you can't do any, you cannot reference everything to the point of contact with the ground. You reference everything with respect to the point of contact with the rope. So you have no slip with the rope contact point, but you have slip at the contact points with the ramp. Drawing these diagrams, and you know, maybe the angles get a lot of fun, are not, there's not much more to them. Okay, I think it's worthwhile sort of ending on this because I've got, well, I've got about a minute and 18 seconds. So this is, again, the last lecture on kinetics. And the important thing is to recognize when to use what term. And people are starting to look, for example, at assignment 8. And you have a curvilinear motion issue that sort of plays a role here. And with problem 1. So translation, sum of forces in x, sum of forces in y, sum of moments about g equals 0. Or you can do the same thing with sum of forces tangential, sum of forces normal, and sum of moments about g. Again, recognize that as long as everything is about the center of mass, the moments are 0. However, if you shift a point and you want to look at some point else on the body, you will have a non-zero moment. And that non-zero moment means you have a sum of moments about A that you don't have about G. A little bit about parallel axis theorem is not out of the air, out of the math. It's coming from a relationship where you have a fixed point against which you can reference everything. Could be an instantaneous